So the submitted material gives us a pretty comprehensive look at Part 2, Technology Foundations for Big Data, covering the stack, virtualization, and cloud architectures.
Okay, let's dive right in then. How can we sharpen this, especially for a technical audience really wanting to grasp the core innovations here?
Right. We could start at the bottom, layer 0, the redundant physical infrastructure. It correctly points out it's needed for volume and velocity, which, yeah, that's fundamental.
It is, but here's the first thought. The way the big data stack components are laid out in Chapter 4, from the physical layer upwards, it would land much stronger if the reason for the architecture was clearly centered on, well, the disruptive economics of it all. Commodity hardware, distributed systems, that kind of thing.
That's a really interesting angle. So what's the specific weakness you see there?
Well, the material does talk about needing scale and resiliency, sure, but it talks about them like they're just standard requirements, Not like the complete paradigm shift that they actually are. A shift made possible only because we started using these massive clusters of cheap commodity hardware.
Ah, I see.
It mentions hardware costs going down, yeah, but it doesn't really frame that economic piece getting scale through parallelism on dirt cheap machines as the absolute main reason the architecture changed so drastically.
Yeah, and for someone deep in computer science, design, that why is crucial, isn't it? If you miss the economic revolution, you kind of miss the point of why the stack even exists. Legacy systems just couldn't do this affordably.
Exactly. So the suggestion is this: reframe that whole layer 0 discussion, contrast it really starkly with the old legacy enterprise systems.
Okay.
We need to hammer home that the resilience here comes from software managing huge numbers of inexpensive, distributed machines. That fundamentally flips the whole cost structure of processing data on its head. It's not just cheaper, it's a different way of thinking.
So the argument becomes, this big data stack is here because it's the only way to handle this data scale without breaking the bank. How do we make that contrast really pop?
Concrete examples, definitely. We need to show the difference. Compare the crazy high cost of getting performance and uptime with specialized, tightly coupled legacy gear, the big SANs, proprietary servers.
Right.
Contrast that with the amazing cost performance you get from just adding more standard, commodity servers in a distributed setup. Performance scales out almost linearly just by adding cheap boxes.
That reframes it completely. It's not just tech specs, it's a strategic shift driven by cost. Much stronger.
And then connect that economic shift directly to the data. Explain that this is what suddenly allowed organizations to keep and analyze data they used to just throw away, like massive weblogs or detailed sensor data.
Because it was too expensive before.
Precisely. If storing and processing a gigabyte of logs cost thousands, forget it. But when this architecture drives that cost way, way down, suddenly that data is incredibly valuable.
Okay, economics linked to data types. Good.
And to really nail it down, use Hadoop. Its two main parts, HDFS, the scalable file system, and the MapReduce engine. They're the perfect example. They were designed assuming hardware will fail and handling it in software, all running on those inexpensive clusters. It shows the economic idea made real in the tech.
That definitely lands the first point with more impact. Okay, moving up the stack structurally. We notice things like virtualization, hypervisors, REST APIs. They felt a bit spread out.
Yes, exactly. Second point. To really cement the link between distributed computing and the big data stack for this technical audience, the material needs to elevate abstraction. Make it clear that abstraction is the key conceptual layer holding these pieces together.
Abstraction. Right, I see the issue. The way it's presented now, abstraction kind of feels like, well, almost like a side effect or an efficiency trick just for MapReduce. Not like the central, independent architectural principle that actually enables MapReduce and everything else on top.
That's the weakness. You've got virtualization in Chapter 5, the hypervisor discussion there, loose coupling with RESTful APIs in Chapter 4. They're all doing the same fundamental job, abstracting away complexity.
Hiding the messy details.
Exactly. Hiding the complexity of the underlying distributed computing model. By scattering them, we lose the chance to explain that these are all different tools computer scientists use to shield the application layer from the chaos below.
So the suggestion has to be structural then. We need a dedicated section maybe? Or at least a clearer conceptual thread.
Yes. Create a clear discussion that pulls these technologies together under that single banner, abstraction. Explain how, together, they hide the network latency, the machine failures, the resource juggling, all that stuff, from the applications and data services. It provides like this conceptual clarity.
Okay, makes sense. And we need examples again, right, to show abstraction working at different levels.
Definitely. Integrated examples.
So take virtualization. How could the existing content on hypervisors be used better to show abstraction?
Explain how the hypervisor acts like a traffic cop. It's this thin software layer managing who gets what resources, CPU, memory, I/O, across different virtual machines.
Okay.
But the key thing, the abstraction part, is that the application inside the VM, it has no idea which physical CPU core it's using. It doesn't even need to know if the physical machine is real or virtual. That ignorance is the abstraction.
Clear. That handles the server level. What about higher up? Network, services. Where do REST APIs fit in this abstraction story?
They provide abstraction at the communication level. They offer this standard, loosely coupled way to talk between services. So when my application calls a RESTful API for data,
It doesn't care where that data physically lives or what OS the service is running?
exactly. The physical location, the underlying tech stack of the service, it's all irrelevant to the caller. It's a temporary link, cleanly separating the front-end request from the messy back-end reality. That's abstraction too.
And this needs to be consistent everywhere, otherwise the whole thing breaks down, right? If one part isn't properly abstracted, it becomes the bottleneck.
Precisely. You have to emphasize that virtualization isn't just servers. It's storage, networks. It needs that end-to-end approach the material mentions to avoid those bottlenecks.
Okay.
This consistency, all the way from the cheap physical hardware in layer 0 up to the processing engine, that's what lets MapReduce and similar frameworks scale almost without bounds, as the text says. So the suggestion isn't just moving sections around, it's about framing it with this core computer science principle.
That really elevates the discussion beyond just listing technologies. Okay, final major area, Chapter 6, Cloud Services. It does a decent job listing the big players, AWS EC2, Google BigQuery, Azure HD Insight, and defining IaaS, PaaS.
Right, but the discussion in Chapter 6 needs to shift gears. It needs to move from just defining IaaS and PaaS to providing a real technical critique. How do these specific services actually handle the tough data trade-offs that come with the big data's V's, volume, velocity, variety?
So the weakness is it's a bit high level. It talks about generic benefits like scalability, elasticity, but doesn't quite get into the weeds of the architectural choices made.
Exactly. Especially around things like, say, transactional guarantees versus raw speed and scale. These cloud platforms made very specific design decisions to be good at big data, often by sacrificing things traditional databases hold sacred.
And failing to discuss those trade-offs means an expert reader might not understand the constraints or why a certain service is suitable for analytics but may be terrible for operational transactions.
Absolutely critical point. The suggestion, then, is to focus the analysis on the specific technical limitations or optimizations of a few key services. Challenge the reader. Make them understand the trade-offs. Are you getting ACID guarantees like in a traditional RDBMS, or are you getting massive scale and speed? Because usually you can't have both, especially not easily.
Right. Need to compare and contrast. So let's make that actionable. What's a good example service to illustrate a key trade-off?
Google BigQuery is perfect. Point out, yes, it runs super fast SQL-like queries on enormous data sets, billions of rows, great for OLAP exploration.
But
Emphasize the key constraint. Generally speaking, data cannot be modified once it's in BigQuery. That's not an accident, it's a deliberate architectural choice.
trading update capability for analytical speed and ingestion velocity.
Exactly. It's prioritizing volume and velocity over the kind of transactional flexibility you get elsewhere. It's fundamentally read-optimized. Highlighting that forces the reader to think about the purpose of the tool.
That makes the architectural priorities very clear. It's designed for analysis, period.
And we should talk about elasticity too. But again, make it concrete. Don't just say it's elastic.
How so?
Explain how elasticity,
Being able to ramp resources up or down instantly enables specific use cases, like running a real-time prediction model on Amazon EC2 that needs to handle wildly fluctuating amounts of clickstream data to target ads. The elasticity is what makes that feasible and cost-effective when demand spikes and drops. Connect the feature to solving a specific velocity or volume fluctuation.
Ties the cloud feature directly to a big data problem. Good. And one last thing here. The connection between these often proprietary cloud services and the open source world, like Hadoop.
Yes, that's crucial for this audience. Mention how services like Microsoft Azure HD Insight actually rely on platforms like Hortonworks Data Platform, which is built on Apache Hadoop.
So even the big cloud providers are building on or offering compatibility with these foundational open source frameworks.
Right. It underscores that the core architectural thinking often comes from these open systems, even when it's packaged up as a slick cloud service. For a computer science reader, that lineage is important. It shows the power and endurance of those original distributed system designs.
Okay, that covers our three main areas for strengthening this section on technology foundations, really focusing on the why and the how, not just the what.
So, just to recap the actionable steps for the writer. First, really drive home the economic rationale. Commodity hardware isn't just an implementation detail. It's the reason Layer 0 looks the way it does. Contrast it clearly with legacy approaches.
Second, elevate abstraction. Define it explicitly as the key computer science principle that ties virtualization, APIs, and other mechanisms together, providing that essential conceptual glue for understanding the whole stack.
And third, get technical with the cloud services. Move beyond IaaS, PaaS definitions. Analyze the specific data trade-offs they make, using sharp examples like BigQuery's read-only nature to show how they sacrifice some things to achieve massive scale and speed.
Right. Implementing these suggestions should lead to a significantly deeper, more robust presentation of these foundations, really hitting the mark for a technically sophisticated audience.
Definitely. We're looking forward to seeing how you incorporate this feedback. Feel free to submit the revised version when you're ready.